Yeah, this is our main goal of synthesis. And why we need to do synthesis? In prior to the manufacturing, we need to um, guess the bugs, right? Prior to the manufacturing stage itself. After the product has manufactured and it went for the fabrication, it's not used. So prior to that, we need to do some bugs. And in this synthesis stage, the tool will optimize the design more when compared to the manual design. So it is a necessary step. We can't do optimization for a lots of gates, right? So that will taken care by the tool itself. And in the earliest stage itself, we can know how the circuit behaves with particular technology nodes. Like in 12 nanometer, the circuit behaves like one, and in 28 nanometer, the circuit behavior is different. So in this stage itself, we will come to know that which technology node we will be going with. So it will optimize PPA, power performance area, which will reduce our chip design cost also. And technology, we need to know about technology independent design and the technology dependent design. In technology dependent design, there are some predefined libraries we will be having. Some like some AND gate libraries we will be having, OR gate libraries, like that. The design is restricted to use those libraries only. But in technology independent design, we can use we are not having any restrictions to use predefined constructs. Okay. Let's go to steps in the synthesis process. The main step, first step in the synthesis is the translation. What will be done in translation? Translation is the process of converting RTL to equation format. From the RTL design owners, we will get some RTL files. Like for the logic itself, we will get some AND gate RTL file, OR gate RTL file, some flip flop RTL files. Like that, we will get those from RTL designers itself. And in the translation stage, what it will do is it will convert those RTLs to a equation format. Means it will convert a basic Boolean equation format, and thereafter it will reduce to some literals. This translation stage is completely independent of technology. There we don't have any technology dependent libraries. So next phase is optimization. In optimization, our RTL code is translated to equation. That equation is optimized in this optimization stage. Means it will optimize to reduce the number of gates. The tool will do as much as it can. And the final step is mapping. It will map to the optimized netlist. Netlist means equations. Those equations are mapped to particular libraries in what we have given as input to the synthesis. Let me take one example. Here we have some example, like we are taking ABC as inputs and Y as output. That Y is A and B or B and C. First, sorry. First, it will do end operation of these two inputs, A and B, and then B and C. Thereafter, it will do OR of both these operations. This is as it is what we have given inside this Verilog code. It will construct a Boolean equation like this, and thereafter it will do optimization. We can do like y is equal to, if we take common as b equal to a plus c, we can write like this, right? So if they, I'm just telling like some example. So it will construct a or c and b. Here it took three logic gates. In this equation, it is taking only two logic gates, which is reducing area, right? So this will happen in optimization, and thereafter these two inputs are given to one OR gate in library, and this whole equation is mapped to AND gate from library we have given. Are you guys following me?
Yes, ma'am.
Yeah. Okay. Yeah. The same way here this example is showing. Next, synthesis flow. In synthesis flow, first we will import all the inputs from the all input files. What are those input files? The input files are RTL code from the RTL designer team and library files. Where we can get those library files? Those library files we can get by Foundry. Foundry, we have a Foundry like TSMC, Samsung, IBM, and global foundries. Those vendors will provide us the libraries. And SDC files. SDC files, SDC file means synopsis design constraints. Those constraints also uh, we will be giving as input to the synthesis. After reading those inputs, tool will elaborate the design. It will read all the design, all the input files. During the elaboration stage, these three tasks are performed. It will read all the input files, RTL files, and netlist file. During this stage only, it will infer some registers. If it is a flip, if we have written as a always at the rate posage clock or negate clock, we will write in the code, right? So if wherever the tool has seen posage or negate, it will convert it to the flip flop, and wherever the tool has seen if or else statement, it will infer mux. And some case statements like if 000 is the input, then output is some 1 or 0 it will take, right? So There it will infer encoders. So on during this stage only, the tool will remove some dead logic cells, combinational loops, floating inputs, unloaded outputs. All all will be taken care in this stage only. In synthesis flow, the next step is reading constraints files, reading SDC. Reading SDC. In SDC means synopsis design constraints. In SDC, we will be having wire load model information, timing information, clock information, and DRV related constraints. Means in this only we'll be having create clock. The, without clock, nothing will function, right? So clock will be created in SDC itself. And DRV constraints are max transition, max capacitance, max fan out. These are also referred as design rule violations. So these are also there in SDC. It will set what is the maximum transition limit, maximum fan out, and maximum capacitance we need to achieve. Based based on this DRVs only, the design should be DRV clean while we are proceeding to the next stage. Okay. And one next step is, so after reading the design, if we are going ahead means we need to check for some sanity, right? And the design quality we need to check. Blindly going into the design, it's not good, right? So we need to check for some quality of the, we need to check for the quality of the design, quality of the net. First we will check for the quality of net list. We are giving library files as input to the synthesis, netlist and library files. uh, we have given the same example. If we have taken uh, uh, if we have taken the same example, we have read the AND gate library, and there is no OR gate library in the design. What what it will do? It will throw a error. It will throw error that the tool is not able to find the library matching to this gate. So it will come under unresolved references. So we need to clean that unresolved reference. We need to provide OR gate library also to the design. Floating input. If input is floating means the design will not be good, right? We need to take care of these floating inputs also. And multi-driven nets. One net is one input net is driving many nets means there will be mismatch in the, there will be some mismatch in getting logic, right? The tool don't know that it is getting either 0 or 1, so it will throw some error. If the design is not perfect. Unloaded output output is not take not given, not loaded, so it should not be there. Combinational loop. If if this output is redirecting to the input, so those also should not present. Check time. These are the quality checks for the netlist. Next we need to check for the timing checks also we need to perform. right? So first we need to check for unclocked registers, UCRs. We have created some clocks and that is not reaching to the sorry, we didn't create clock for this specific register, for the register, so it will not give proper result. So we need to create clock. We need to check for which register is this and the input port coming from this. For that input port we need to create clock. Timing loops also. Yeah, any queries?
Participants, do you have any queries? No, madam, you can continue.
Yes.
Ma'am, good evening,
Timing.
ma'am.
Yeah, good evening.
Ma'am, SDC is a synapses design constraint or it is a synthesis design constraint?
No, synopsis design constraints.
So SDC is in metric office also we can get it, right? So how can we then say that it is synapses oriented? Just I have a small query about this.
Sorry, I didn't get you.
So generally the
Huh.
tools, synapses is a kind of a vendor.
Yeah, yes,
Like
yes.
synapses, there are many other vendors also there to
Yeah.
write the concept of the program. So those vendors also will provide the SDCs, right? So I think it is a, I mean, as of now, it is a synthesis design constraint. Just want to clarify it about it.
It's synopsis design constraint only, but that constraints are not provided by vendors like synopsis or cadence.
Hmm.
We will maintain our own
Exactly.
constraints, right?
Exactly, exactly. That is the only I am telling you that. So the design constraint we are writing in a platform which is provided by the tool. So we cannot
Yes.
adapt to the particular vendor name. It seems probably right.
Yeah, yeah, yeah. Yes.
Yeah. Thank you, ma'am. Thank you.
Yeah. Yeah. Next is we have created clocks and it's not reaching to all sinks. Means it's not it will not give proper result, right? Clock should reach to all sinks to get proper output. So we need to check that also. And unconstrained endpoints. And all the endpoints should be constrained with either IO delays, IO delays, or some constraint should be there for all endpoints. And missing IO delays for ports. Um, if let us say this is one block, this is another block, another sub block. This is all top level. This is top level block. So some input is coming from here and it is going here, going through some port, output port. It is going to this input port, and from this output port it is going top level. So we need to take how much input delay it is taking here, how much output delay we are getting for this block, to how much delay is getting, how much delay is taking to reach this input. So those constraints should be there for all IO ports. Okay. Yeah, after all these checks are clean only, then we need to proceed to next step. Otherwise, we need to come from beginning itself. Okay. And next step is generic mapping. Generic mapping means the Boolean equation which we got is mapped to library cells which we have given as input. Yeah. This RTL code to the gate level netlist representation. This maps to the cells to generic library which is technology independent. Here the mapping is technology independent. And some logic optimization also done by the tool here. After this it will do technology mapping. After this generic mapping it will do technology mapping. What will do in technology mapping? It will map to the targeted library files which is having power information, timing information. Timing information means rise time, fall time, leakage power, and area constraints. Lib will be having this timing and power information, and we will provide left also. We'll discuss about that after some time. Optimization. It will do optimization next. During this optimization, it will follow PPA, power, performance, and area. I will discuss some of the optimization techniques now. VT threshold voltage. While giving tool, while starting the synthesis itself, we will provide some VT flavors of libraries, different VT flavors of libraries, so that during the optimization stage it can swap easily. What are the VT flavors we have? LVT, uh, LVT, HVT, and SVT. LVT will give us low delay, and it will give high leakage. HVT. HVT stands for high threshold voltage. LVT stands for low threshold voltage. SVT stands for standard threshold voltage. HVT cells give high delay, and low leakage. SVT is moderate to LVT and SVT. While performing timing optimization, tool will consider low LVTs and it will consider leakage also. It will perform both leakage power aware and timing aware synthesis. So it will swap based on violation we have. If we have more timing violations, it will opt for low LVT cells. If we have more leakage violations, then tool will opt for HVT cells or SVT cells. Okay. Next, upsize or downsize. It will do upsize or downsize based on the violation. Upsize or downsize means how the library cell will be like. If it is AND gate, it will be like AND 2 or 3. 2 or 3 represents 2 input or 3 input. Let's say 2 input. X stands for drive strength, 4P, 5P, up to it will be like a 72P. Those are high drive strength cells. Mostly we will in lower technology nodes we will use up to 10P only. This 4 represents the driving capability of a cell. For timing violation, if it is having more timing violation, then the tool will swap to the highest driving capability cells, so that it can have low transition time, less transition time. If 4P cell behavior is like this, if it is
Ma'am, what
like
is the
this,
meaning of 4P?
4P,
4P, what it is? Yes,
4
ma'am.
stands for drive strength. This is the drive strength of a cell. 4 stands for 4P0. Let us say 4P0. We will be having some cells like zero point 0.5 drive strength also. 1P5, 4P0. Mostly these zero point 0.5 cells, 1.5 cells will cause some DRC issues. So mostly we will go for 4P 4.0, 6.0. This 6 drive strength, 4 drive strength only. This 4 represents drive strength, driving capability of a cell. Okay, got it? Huh?
Okay, ma'am.
Yeah. Based on that drive strength only, we will be having that transition delay. The delay of the cell will change based on that drive strength. If the transition time of a 4P cell is like this, if it is the timing window, it is taking more time. Let us say that 4P cell is taking 20 picoseconds to reach from input to the output. Okay. If we swap to that with 6P or 8P, the delay will get reduced to some 15 picosecond or 12 picosecond. Means this transition time will change. We will get input quickly when compared to low drive strength cells. Ideally, we can't get input as much as possible, right? At 0 seconds, it will take some delay, right, to reach from input to output. So that delay will get changed. If we have used high drive strength, the delay will be less. Low drive strength cells will give high delays. This is based on transition time only. Okay. Buffering. Buffering. If one cell is sitting here and another cell is sitting here, these two cells are connecting like this till this is taking time, like this is taking 10 pico. Let's say 10 picoseconds to reach from this pin to this pin to this pin. Let's say this time is 10 seconds. Sorry. Let's say we will say 100 ps. This is taking 100 ps. Let us say 100 ps is more. This is taking more delay, right? So we need to reduce the delay, and this length of the net is also too long. It is around 400 microns. So 400 micron is too long. From 0 to, let's say it is 0, sorry, let us say 1. It is carrying logic 1. Let's say logic 1 is 5 volts. From reaching this pin to this pin, the transition time is more here. So it will fall down to something around 4 volts, or some cases it will fall below this also. So sometimes if it falls below this, the output also will get changed, right? So this behavior also will get changed, circuit behavior. So we don't need that type of behavior. So what we will do is we'll add one buffer here. This buffer will strengthen this signal. After adding this buffer, the tool behaves like it till here to here. It will be like, if it is starting at 5 volts, it will fall around 4 volts. So again, if this buffer will make it as 5 volts, this buffer will boost in this signal, and then it will reach the proper logic will reach here.
Madam,
Yeah,
your
yes.
screen is not visible, madam.
Oh, is it?
Ma'am screen is visual. Maybe internet connectivity is less, ma'am.
No, madam, actually you're teaching on pain, madam.
Yeah, paint.
Yes, that's what you can see, madam.
Yeah, you are able to see, right? Okay, something
Yes, ma'am.
network issue, I guess. So 5 volts to, without this buffer, it is going to 3 volts. After adding this buffer, this will strengthen the signal. It will be like 4 to it will do this.
Please
5
continue, ma'am.
Yeah, yes. This will strengthen the signal, and proper logic will reach this circuit, reach this node, input node. Cloning means it will duplicate. It will
Ma'am,
duplicate.
excuse me.
Yeah, yes.
If we add buffers, then the delay will increase. If the delay will increase,
If that is based on the net, means this net length is more, right? If this is causing more delay here, it will consider net delays and cell delays also, right?
actually, without using that buffer, if it is, if we are getting 100 picoseconds delay due to that wire, if we are adding buffer, then it may increase, ma'am.
No. What it will do is, the delay is directly proportional to length square, I guess. Some length square. Let us suppose delay is here some constant into length square. Let us say 400 400 microns delay. Here delay is getting half, right? Sorry, length is getting half here after adding that buffer. If you have we can say that we can add exactly half of the length of the distance. Okay, then our new length is length by 2, right? From one node to another node, this is length by 2. We reduced it to half, right? So delay will be like L square by 4. So delay also will get reduced. That depends on the violation we have. If it is based on the net length, if the violation is causing based on the net length, then buffer insertion is good. Okay.
Okay, ma'am.
Are you agree my point?
Yes, ma'am.
Yeah. Yeah. Cloning. In cloning, what it will do is it will duplicate the cell. Let's say this is our complete design. One cell is sitting here and it is having too many fan outs. And the same cell is driving one cell here. Let us say, for suppose, the same cell is driving this cell also. Some A. This is some A. This is some B. Sorry, this is B. This A cell is driving some other cells and this B cell also. From here, from the top of the this chip to it is driving some cell at the end. So it will be difficult for this cell to drive this long, right? So we will duplicate the cell, same cell A here, and we will connect this net directly to this. This way we can reduce this net length so that our timing violation also will get reduced. For this fan out splitting also we can add buffer. Let us say our max fan out limit is 4. But this cell is driving 5 cells. So it is violating our rule, right? This is violating our DRV violation. Our max fan out is 4. But this cell is driving 5 cells. So what we will do here in this case, we will add one buffer after 2 cells or 3 cells. So that now what this is doing, this cell is driving this cell, and this cell. The fan out of this cell is 3. Now This is driving these three cells. This one, and this one. So this fan out also 3. So our fan out constraint now got resolved. It is obeying our design rule violation. Sorry, it is obeying our max fan out constraint. Any doubts still here?
Ma'am, when we are adding buffer, if we require more number of outputs, we have to connect than the fan out. Then again, we have to check buffer fan out also.
Yes. While inserting buffer, we will check for that buffer fan out also. That also should not violate our constraint, right?
Okay, ma'am.
That also actually that also taken care by 2. Okay. Yeah. Till this cloning we have done, right? Okay. Other than cloning, what it will do is logic restructuring. Logic restructuring means um, it will do if there is AB plus some logic optimization it will do, and it will map to that corresponding output. Next, we will see about physical aware synthesis. In synthesis, generally we will have logic synthesis and physical aware synthesis. For the first time, while we are doing synthesis by taking inputs from the RTL files, we will do logic synthesis only, as we are not having any input to the PD guys. So first we will do logic synthesis. That netlist, that output, we will be getting some one output netlist, right? Combining all that netlist and SDC, we will give to the PD team, physical design team. With that synthesis netlist and SDC, PD team will do floor plan. They will arrange all the macros and IO ports. If it is a power domain based design, they will add those power domains also, and the def will be given as input to synthesis again. This is called as physical aware synthesis. For physical aware synthesis, we need all physical libraries. Physical libraries means lefts. Left will give us the physical structure of a cell or some macro. It will give us physical structure. So we will take physical libraries and timing libraries also. Along with the timing libraries, we will take a physical libraries also. And the main key role in the physical aware synthesis is a floor plan def. We will take the floor plan def as an input. Design, we will take UPF also as an input. Okay. What are the outputs? Let us see outputs generated from synthesis flow. We will get optimized gate level netlist and SDC as discussed, and reports also. We will get timing related reports. Till now, till synthesis and PNR play stage, we will see setup timing only. In timing, we will check for 2 types of timing violations. First one is setup and second one is hold. Why we will not taken care about hold here is hold hold will be considered after the clock propagation only. So before place and throughout the synthesis, we will focus on setup timing and DRV optimization only. Tool will take and care this setup and DRV optimization, and power reports also we will get, and area report we will get for corresponding cells for AND gate. For 2 input AND gate, this much area is utilized, total area, and we will get some detailed report also. For AND gate, this much area utilized, and for CG clock gating cells, flip flops, how much area is utilized, we will get some detailed report. Regarding this timing violations also, we will get detailed reports. And after we have provided netlist to the PD team, if they has any issues with memories or something, they will get back to synthesis. Synthesis will take care of those memories by swapping to some other memories, or changing VTs. Memories like we will say 1096 by 122, like that will be there, right? If PD people will not able to optimize the design with that memory, synthesis people will split that memories to two, or it will combine memories, two memories to one memory. All this will be taken care in synthesis only. So after the synthesis, we will point synthesis netlist to DFT team to detect manufacturing defects in the design prior to the fabrication itself. So DFT team will test the design here itself, and they will add some scan chain insertion during this process to test the to increase the testability of the chip. They will add scan chains and some extra logic also in the design, so that we can get defects prior to the manufacturing, prior to the fabrication only. After this also, we will have one incremental optimization. So that finally what PD people will take is scan inserted netlist only. PD people will do tape out with the scan inserted netlist. Synthesis netlist will be given to DFT team. DFT team will do scan insertion. That scan inserted netlist will again come back to PD team. Okay. Any doubts still here?
If anyone have any doubts, you can ask. You can continue, ma'am.
Yes. Yeah, till now we have seen timing optimization techniques and area optimization. Area optimization means gate reduction. Optimization, in optimization only the area will also get reduced, right? So area reduction techniques and time reduction techniques we have seen, like VT swap, cloning, buffer insertion, all these. And now we will go for power estimation and power analysis. During the synthesis itself, we will do power estimation, but it is not the exact one. It's the approximate one. We can't say precise calculation here, because power depends on resistance and capacitance, right? So in synthesis stage, we don't have real resistance and capacitance. This is a synthesis stage is a ideal network. Ideal. So resistance and capacitance, no resistance and capacitance values. So we will do approximate calculations here. Okay. So this can help us in future. In future, what what the techniques we will be having to reduce that power. If it is high in the synthesis itself, we can reduce that by adding clock gating techniques or power gating techniques and some resource sharing. So, so here itself we can reduce power somewhat we can reduce power here itself. Okay. And types of power estimation in synthesis. Uh, Types of power estimation. We'll be having dynamic power estimation and static power estimation. Dynamic power estimation comes into picture where the input or some signal is transiting from 0 to 1, either from 0 to 1 or from 1 to 0. Means it is switching from 0 to 1 or 1 to 0. So it is basically based upon switching activity, or else we can say toggle rates. Okay, we might have gone through in our engineering course like that dynamic power estimation directly depends on frequency, supply voltage, and switching activity, right? Some power equation also we will be getting. Dynamic power dissipation is equal to is proportional to F frequency, load capacitance, and supply voltage VDD square. In our engineering basics, we might have learned this. After removing this proportionality constant, we will be having one constant which is called as switching activity factor. This will count from how many are switching from 0 to 1 or 1 to 0. So our dynamic power dissipation depends on frequency as mentioned in PPT. Frequency and supply voltage and load capacitance of gates. And next one is static power dissipation. During this stage itself, if the dynamic power is more, then we will be focusing on frequency, whether we need to increase frequency or decrease frequency, how the load capacitance are acting, supply voltage. Here only we will decide all these factors. This factor we can decide. This factor also we can decide. This load capacitance is based on the design, right? We can't we can't change it here. And next one is static power dissipation. Static power dissipation means when the circuit is not functioning, when there is no functioning, the circuit will be uh, on the, there is some leakage in the circuit, so that comes under static power dissipation. Static power dissipation is due to because of VT, threshold voltage, subthreshold voltage, and channel length, right? So we can change these VT flavors for that static power dissipation. Yeah, as mentioned, it is not precise one. After the PNR implemented, PNR routing stage completed, we will be having real routes and real nets. It will give proper RC values. So that,
Excuse me, madam.
yeah, yes.
Someone raised hand. Is there any doubt? Okay, madam. Continue.
Yeah. After physical design complete completed, route stage completed, we will get a real nets comes into picture. Then only we can estimate the real power value, real timing issues. We will face real timing issues and real power issues there only. Next. Yeah, as said, types power analysis types: static power analysis and dynamic power analysis. Static power analysis. Static power analysis is when the circuit is not functioning, it will come from subthreshold leakage or some transistor parameters like voltage, sorry, width, length parameters like that. Dynamic power analysis will be dependent on switching activities. Vectorless power analysis and vector based power analysis. Vectorless power analysis is this will estimate power without applying any input test vectors. This is useful in early design stages with incomplete input data. Yeah, vector based analysis is we will pass some test vectors to determine the power power details. Yeah, and we come to conclusion. As we discussed, this power is completely accurate power analysis comes into picture after the physical design routing only. After the routing happens, then only we can find proper power analysis. There only we can do proper power estimation. And switching activities also should be there. And one more thing is, in synthesis also we can read the switching activities with one input file, like safe file. We will call as safe file. Safe file. This will give us switching activity information. Switching activity. This safe file we will get from power team. From the power team, we will take this as input to the synthesis so that we can get proper toggle rates. And in PNR also, we will use the same safe file for the proper power analysis. Okay. If we have seen the commands to read the input files, means to read the Verilog files which are there in .v or .vhdl format or system Verilog format, we will use read HDL to read the RTL files and elaborate elaborate the design. It to read all the inputs means RTL code and .lib files. After that, it will do elaborate the design. Thereafter, we will check for the sanity checks. Okay, sanity checks after reading SDC also. After reading SDC only, we will do sanity checks. and generic mapping is done with syn generic command, and technology mapping is done with synmap command. Optimization will be done with synopt. This synopt is only for logic synthesis. If we are doing physical aware synthesis, we should use hyphen physical. Af- After this, we will give to DFT team. We'll get a netlist. We'll get netlist with these commands. Write HDL and write SDC. These two, netlist and SDC, we will give to netlist will be given to DFT team. After scanning session, that will be given to PD team as well as with the SDC. This timing report, area report, and power report are for our confirmation, uh, for our checking purpose only. Thank you. Any doubts here till here?
Good evening, madam. I am Dr. V. Adnarayana.
Yeah, yes.
Yeah, as you told that about the static power analysis,
Yes.
uh, threshold voltage is one of the reason how it is.
Yeah. The circuit should function after some VT level only, right?
Yeah,
This is our MOSFET. Let us say this is our
okay,
MOSFET, and we are giving some input at gate level, so gate terminal. We are giving some VT as 0.7. Okay.
okay.
In some cases, the circuit is not functioning means this is not on. This transistor is not on means
Mm,
less than some VT.
mm,
Okay. Less, if it is less than VT also, if the circuit starts functioning means
mm,
sub threshold, less than threshold voltage, and the circuit start functioning, then it will
mm.
comes under um, leakage, threshold leakage.
Okay, okay.
Yeah.
Thank you.
Yeah. Anything else? Not only on synthesis, you can ask me in PNR also. If you have any idea on PNR, you can ask me. I will clarify if I know.
Madam, I have a doubt regarding upsizing and downsizing.
Okay.
Uh, uh, while performing our analysis, how could we identify that these particular cells are to be done either upsizing or downsizing, or how can we recognize that?
Okay.
Commands or any commands to convert upsizing and
Uh,
downsizing. So,
yes. Let me explain in a minute file. Yeah.
as
I
we will be
told.
having
Yeah.
many number of cells, no, most
Yeah.
probably more than 10,000 or like that. So,
Yeah. We'll
like,
be having millions of gates
yes,
here.
yes,
We'll be
cells,
seeing.
cells
Cell
also
means.
in that count, in that million count.
Cells means in the sense of gates. We will term as gates here in our industrial terminology.
Yes, yes, yes.
We will
Okay,
term
so
as
how to
gates.
identify that a particular cell can be either upsized or downsized, like that?
Yeah. I said that report timing, right? Report timing. It will give complete detailed report. Report. One more thing is while doing optimization, we will tell the tool to optimize, which paths to optimize. Okay, let me explain first. What are the path groups present here? Present in our design. Suppose, let us say this is one register and this is another register. These two are connected through some logic. Some logic here. This is D terminal, D pin. This is Q pin, and this is going to this D pin, data pin. Here we will give clock. Let us say these two are triggering with same clock. Let's say clock 1. Some input is given to this D pin. This is going from this clock Q to through set of some combinational logic. This from this to here, this is some combinational logic. So this path group is termed as register to register path group. Okay, and reg to reg, in industrial terms we will call it as reg to reg path group. Reg to one more path group we have is reg to output port. Reg to output port. It is going this register to output port through some set of logic here. And we will be having from input to register.
Yesterday we learned about these 4 path groups, madam.
Oh,
We
okay.
have
Okay.
a bit
Already
idea
done.
about this.
Okay. So, okay. While doing optimization, we will tell the tool to optimize which group to optimize, and weightage also we will give. For reg to reg, I will say weightage will be 4. Reg to mem, weightage, same weightage. First times it I'm saying same weightage. Mem to reg, 4 weightage.
Where we will specify these weightage, madam? At what stage?
Before to optimization, we will do group path. Group path will give some commands to the tool. Group path hyphen from all register to all registers. Then it will pick reg to reg path.
Okay.
Or else group path hyphen name reg to reg. Like that we will give. Or next group path register to, we will filter memories from all the cells, and there we will give this weightage. Mem to reg also same way, and inputs to register. Mostly we will give high weightage to these paths only. Reg to reg, reg to mem, and mem to reg path groups. So while the tool will keep in mind that all these path groups and do optimization. If we have do report timing hyphen path group register to register, tool will give some set of report. You have you ever seen some timing reports?
Uh, Actually, I have a bit idea.
Okay. So what it will contain is start point. Let us take some rest to rest path group. Start point as register, end point as register, and with which clock it is getting violated, and from start point to till end point, what are the cells present in between. AND gate, OR gate, set of gates will get, right, will have, this will have all this start point. For the start point, how much delay we are getting. After that, let us say some instance one with AND gate. This delay also present. Delay, transition time, and incremental delay, or arrival time, we can say. Arrival time. Do you know about arrival time? What is
Yes, madam.
arrival?
Arrival
Uh,
time. Yes, madam.
yeah, okay then. Arrival time also it will be there in report. So here, what arrival time will be like this delay plus this cell delay. It will come here, and next some gate like B. This cell delay also will be present. Total delay will come in arrival time. Tool, but in report timing we will get instance name and that cell name, ref name also. Ref name means I have I told you, right, with the dry strength it will give. So based on the dry strength and delay, we can say whether if the path is violating, then we can check for the cell VT class or cell dry strength. If it is high VT, if it is high VT cell, we can swap it to low VT. Or if it is still in low VT, then we will check for the dry strength, of the cell. 1 second, we'll plug in charger. So based on the delay, we can say right, delay and dry strength of the cell, whether we need to swap or not. We can check in the timing report.
Okay.
Got
Madam.
it? Huh?
Okay, madam. Thank you.
Yes. Next, any question?
Hello.
Yeah.
Madam, what type of errors we can expect during DFT, madam, testing during that phase? What type of
Sorry.
general errors we may
Come
expect?
again. Come again.
DFT. Scanning that we'll do no during that testing procedure. Actually, in the
Yes.
front end during compilation and simulation, we'll have the syntax errors and functional errors. So during DFT stage, what type of errors we can expect?
Yeah. During
Can
the
you say at
DFT
least
stage,
one?
we can check. Yeah, we can check for stuck at false. Stuck at false means the design is to, it should be logic 1, but the design somehow it is giving logic 0.
Yeah. We have some idea, ma'am. We have some idea about
Yeah, those faults will be captured at DFT stage.
it. Oh.
that detailed concept will cover by someone, I guess, later.
Okay, ma'am. Okay, thank you.
What else I missed? Do you all aware of wow, what is a left file contains, library contains, technology left? Do you have idea on that? Hello?
Please continue, madam.
Yeah. Do you have any idea on technology left files, library files, or need to explain?
No, ma'am.
No. Okay. While starting the design itself, after reading the before reading the netlist itself, first we need to read technology left. There are 4 types of left files. First one is technology left. Tech left. Next, macro left. Next one is standard cell left. Next one is IO left. IO ports or IO pad. To say. Technology left contains all metal layer information. Any doubt
ఇది
or
సెల్స్ డిలేస్ పెరిగితే సెల్స్ చేంజ్ చేయాలి అని చెప్పింది. ఆ సెల్స్ ఎలా చేంజ్ చేస్తాము, అసలు ఏ సెల్ చేంజ్ చేయాలి అన్నది ఎలా తెలుస్తుంది? ప్రోగ్రామింగ్ వైజ్
ప్రోగ్రామింగ్ కాదు, మనకి లైబ్రరీస్ ఉంటాయి డిజైన్ లో. హలో, సమ్వన్ ఇస్ స్పీకింగ్. హలో,
Ma'am, you can continue, ma'am.
okay.
Hello.
Yeah, yes. Yeah, technology left contains how many metal layers are there, and what is the metal layer direction. Usually we will be having like HVH or VHV metal stack. HVH or VHV metal stack. If the first layer M0, if we have a, let us say it is a 10 metal layer stack. So if the first layer is horizontal, let us say M1 is horizontal, then M2 will be vertical and M3 will be again horizontal. This is HVH stack, and follows like this. Next one is vertical, next one is horizontal, like this. And VHV stack is the first one is vertical, M2 will be horizontal, and M2 will next be vertical. Like this, we will be having metal stack. This all info will present in what is the metal width, metal layer width, maximum width, minimum width, spacing. Those everything will be present in technology left. Next, macro left. Macro left means pins in which layer, macro pins in which layer, and blockages are in which layer. Blockage or abstract we can say. Like this info will be there in macro left. This standard cell left means standard cell related macro, standard cell related pins, pin layers, blockages. What is the height and width of that macro or standard cell? Likewise for IO cells also, pads, IO pads also. This information we will get in left. Let us say if you have read netlist without reading techleft, what will happen? Can anyone say? Are you guys following me? Or you need any
Yes,
clear
ma'am.
explanation? Is it able to understand?
Yes, ma'am.
Yeah. If we have read netlist without reading this techleft, it will throw error that these layers are not present. Um, Sorry, without reading techleft, if you have read all macro left, standard cell left, IO left, netlist, it will throw error that this metal information is not present. So first we need to read techleft. Likewise, lib files also. Here we have only three types of lib cells. There is no technology lib, tech lib here. Only macro lib, standard cell lib, and IO lib. So what a lib file contain? It will contain timing info and power info. Timing and power means it will give some rise time, rise time of a cell, fall time, leakage, and some lookup table, cell delay lookup table. It will contain. Next, SDC file. SDC file contains create create clock command, DRV settings like set max transition, minimum transition, max or min transition, we can say. Max fan out limit, max capacitance, max or min capacitance, IO delays, set max delays, set input or output delay. It is defined on ports. And along with the created, we will be having some generated clocks also. Some exceptions like set false path, multi-cycle paths. We need to set. Otherwise, if tool will result in more timing violations. Like etc. etc. Next, UPF. UPF will contain power domain info. Let us say we have 2 or 3 power domains in a single design. This is a single design. In this, we will be having this as one domain, and this this is operating at another domain, at some other domain. So we need to tell the tool this domain is taking which voltage and what are the cells present in that domain. That supply net we need to give, and connection also we need to specify to which power net. That whole information will present in UPF file. These islands we need to create in floor plan. This will be done by PD people. If it is a power domain design, we need to take UPF in synthesis also. Okay. Any confusion till here?
Is anyone
Speaker
having any
guys.
doubt?
So you guys are not understanding.
Yes, ma'am.
Understood? Huh?
Yes, ma'am.
Regarding synthesis, PNR, but I have a limited knowledge on DFT. I'm able to tell your doubts on synthesis, PNR, and timing. Okay. When it comes to these are all genus commands. When it comes to design compiler, these commands will change. In design compiler, it will do like analyze, elaborate, and compare. I guess analyze, elaborate. Analyze means it will read all the all the input files. Let us say, instead of saying RTLs, lib files, we can say all the inputs. In analyze stage, do it will read all the input files. And next, elaborate stage, it will do like same mapping, optimization, everything it will do in elaborate and compare the results. Some slight changes in commands only. Algorithms wise, some changes will be there. That's everything will be same.
Hello, ma'am.
Yeah, yes. Yeah, tell
Is
me.
your presentation is over?
Yes, yes.
Okay, ma'am. Participants, do you have any queries?
No, madam.
Okay.
Shall
Okay,
we?
ma'am.
y- Yeah,
Ma'am, would you like to continue?
yeah, yes.
Okay, ma'am, continue.
If they have any doubts, we'll continue or we will wind up the session.
Okay.
At least did you got my point? Do you have any idea? Did you get idea on synthesis? What it will do? Everything? Can anyone?
Yes, ma'am. Yes, ma'am.
Okay. Then you understand, right? You understand the concept, right? Okay, then if you don't have any queries, we will wind up the session. Thank you.
Krishnavani, madam.
Okay, sir.
Okay. All the participants, just wait. Our second speaker will join in 2 minutes. All the participants,
Madam,
please wait for a minute.
thank you so much for your lecture, and it lecture is quite interesting, and all the participants they learned about this synthesis. Thank you for accepting our invitation, ma'am.
Thank you. Thank you very much.
Thank you, ma'am. Thank you so much.
Sir, just
And
wait, sir.
yeah,
So, once again, good evening, all of you. Today, our second speaker is Udaykumar. He is having more than 5 years of experience in physical design, and now he is working as a senior engineer in Tessolve Semiconductors. Now, I am handovering this session to Udaykumar, sir.
Good evening, sir. Welcome to our session, sir.
Yeah, good evening. 1 minute. Can you able to see my screen?
Yes, sir.
Yes, sir.
Hello.
Yes, sir. You are audible
Yeah.
and your screen is visible.
Yeah. So I am Udaykumar. So I'm from Tessolve Semiconductors. So I have 5 years of experience in PD. So physical design. So so can I start from PNR or need some introduction about synthesis?
You give just
You
introduction and
already
start.
listened.
Yeah. So so this is the ASIC design flow. So first we have system specification, then architectural design. So these things are already covered, I think so. So now I'm going to cover about PNR. So before PNR, we have synthesis. So synthesis is nothing but we are converting RTL to gate level netlist. So RTL, you know already, it is a VHDL program. So it was converted into gate level netlist. How it was converting means, so we have some methods for converting. So this is the RTL code. So this RTL code is converted into basic logic gates. So basic logic gate without timing information. So then it was optimized. So it was optimized, and we have a target technology that is gate level network. So this is the synthesis introduction. So so basically for PNR we are giving input as gate level netlist. So it will be taken from synthesis. Next we can go for PNR. So this is the PNR architecture. Can I able to see my screen?
Yes, sir. It is
Yeah,
showing synthesis slide, and now it is showing that flowchart,
yeah,
PNR flowchart.
yeah, PNR. So this is the PNR architecture. So first we have design initialization. So first we need to initialize. So what are the inputs we needed? What are the partitions we going to set up? So we need to first of all we need to initialize that thing. So after that we are going for floor planning, power planning. So placement optimization. So later steps I will explain what are the deep knowledge about these things. So first we are doing floor planning, power planning. Then we are placement optimization. So clock tree synthesis and optimization. Then we are going for routing optimization. Then metal fill we are doing. Then RC extraction, stress extraction. So after stress extraction, we are doing SPA static timing analysis. So side by side, we are doing physical verification, DRC, LBS, and diagnostics. So these things will cover in PNR. So this is the major things we are using for our project. So physical design. So physical design is nothing but we are converting the netlist into our physical layout. So that is in GVSI format. So physical design is process we can say as PNR, place and route. So mainly I will show. So these are the input files we needed for PNR tool. So we have one block. So we need to do some steps in that block. So for that we need some input. So we here have netlist, then list, then lib, then SDC, EF. So these are the some files we needed for uh, approaching for the floor plan. So any doubt till this?
Sir, .vg means what kind of extension it is, sir?
It is also it is a gate level netlist. It is like we are converting VHDL to gate level netlist now. So dot V only.
Dot we were aware about .v, but
Dot V only.
.vg we don't know about that.
It's some it's like it's due to some Intel where they are using dot V. Some Qualcomm they are using dot VG. So some different companies they will use different types of formats. So basically in synthesis we are using lib. For cadence we are using .db. So different types of EDA companies also they are fixing the name for particular files in some different formats. Okay, so we can say gate level netlist .vg like that.
Understood, sir.
Yeah. So these are the inputs for PNR. So after loading these inputs, how our design it will be. So this is my actually I'm doing some projects. So first, before going to floor plan, we need to estimate our height and width of our die. Okay. So after that, we need to define our IO area. So how many input ports, how many output ports, how many input output ports are there. So we need to initialize before starting our program. Okay. So floor plan involves um, placing input output ports, then creating standard cell rows, then placement of macros, then creating placement blockages, halos. Then after floor planning, we do power plan side by side. So these are the four plan steps I am doing in my project. So how the height and width of the die is calculated. So the top team, the full shift team will view the height and width of particular block so that we can take that those things and will take the block size. So how the width and die is calculated. So after loading all the inputs, after giving initialize the floor plan, so like this we will get. Can you able to see this? So it is real time project. Okay. So don't take any screenshot. So actually this is our block. Okay. So I have 254 macros. So the 254 macros are sitting outside. So we are giving the initialize floor plan. We are starting the initialize floor plan when we are creating this area. Okay. So the area we have X1, X2, Y1, Y2. In side lines we are giving. Then we are flipping the rows. So that after giving this command, the block was created and macros are sitting outside. So these are the macro guidelines we need to follow. So macros should be placed at the priority of the block. So we have some guidelines to follow to place the macros. So after placing macros, we need to place the macro based on the hierarchy. So I'm having seven hierarchies. Okay. So these are my hierarchies. So based on this, I am placing the macros. Okay. So this is some screenshots. Oh, So so these are some screenshots I took for my real time project. So I have placed the macros like this. So after placing the macros, we need to create the encapsules, well capsules. So capsules why we are using for latch up issues. Okay. For encapsules we are using for enable continuity. So after doing floor plan, we need to do power plan. Okay. So macro needs VDD VSS. So we are doing such a power plan. So first we are creating some PG strategies. So while placing the macro, we need to see the fly line. Okay. So some macro will contact with some ports or macro to macro. So whichever it's connected, so we need to place them nearby. So that in future, in placement stage or routing stage, we need to avoid interconnect length or routing resources. So for that, we are connecting, we are keeping the macros nearby. The ports are nearby the macros which are talking with each other. So after placing macro, we need to give halo, keep out margin for all the macros. So that what happen means in placement stage, the standard cell which are talking with the macro will come and sit nearby. So to avoid this, for if we come and sit nearby macro means congestion will exist. If congestion is more means the sort will be more, then we can't able to do sign of PV things. So we need to do halo for all the macros which are placed in our floor plan stage. So macro, we are putting a halo for macros in four sides. So while placing macros, so we need to see the crisscross connection. We should avoid the crisscross connection when placing the macros. So these are some examples for the ports which are connected to the macro. So we need to keep that macro nearby the port. So the macro to macro connection. So this is a good floor plan. So this is a macro RAM. It is a macro. This is also a macro. So this is the standard cell area. So it should not touch or it should not interrupt the macro. So if it is the standard cell is okay, a good floor plan is initialized. So power planning, we need to do power plan. So power planning involves the calculating number of power pins, number of rings, stripes, width of the ring. We need to check the IR drop, whether static IR drop is more or dynamic IR drop is more. We need to avoid that. So we are doing this those power planning. So this is our block. Okay. So for power planning, we are divided into like this. So this is the power rings. Okay. You can able to see the power rings. This is my block. Okay. So in center of the die area and core area, I have some power rings. Okay, these power rings distribute the powers to my full block level. Can I able to see this power trunks, power pads. Through power pads, I'm getting power to power rings. Through power rings, I'm giving to stripes. Okay, so this is the way for power distribution architecture. So trunks connect, it connects and mesh. So these are some power strategies we are following. Trunks mesh level via. So this is the IO ring. So this is my block. Okay. So this is the IO ring. So IO ring is nothing but the power rings is formed by IO ports. We are giving power to IO ports. So this is chip level. Okay, the full chip level it will be like this. So this is one block, this is one block, this is one, four blocks are there. So block level, I'm giving power like this. So from rings, I am distributing to straps and rails. So this is the way the power was distributed to overall block. So next is placement. So after placing the macros, so first floor plan and power plan was covered. So what basically we will do in floor plan means we are placing the IO ports first, then we are placing the macros, then we are creating the standard cell rows, and after doing this, we are going for placement blockages. Then we are allowing halos. So after these things are completed, we are going for power plan. So by using stripes and rings, we are distributing the powerful block level. So after these floor plan and power plan done, we are going for next stage is placement. So placement is a very important after floor planning stage. So placement is nothing but we are placing the standard cells. Okay, the tool itself will do this placement. Okay, so the macro, the standard cells which are talking with those macros, it will come and sit nearby. Okay, so Placement is the stage we are placing the standard cells in the design. So placement has several steps, that is pre-placement, initial placement, legalization, removing existing necessary buffers. So what is pre-placement? After floor planning, so we need to insert tap cells or boundary cells. Okay, tap cells why we are inserting means to avoid latch-up issues. Okay, so boundary cells we are taking for n-well continuity for avoiding DRC violations for further stages. So we need pre-placement should be done before the placement. Okay. So next is initial placement, that is course placement, that is global placement. Okay. This is a rough level of placement. Here we are placing the standard cells roughly. Okay. Here we are not seeing any spacing or any DRC issues. Okay. So the standard cells are sitting nearby or it will be overlap. So course placement is nothing. We are placing the standard cell in a standard cell rows which we are created in a floor plan state. Next is legalization. So legalization only we are placing the standard cells in accurate places by giving proper spacing and a proper standard cell rows. We are placing the macros. So legalization. So after that we are seeing HFNS. So high fan of businesses. Okay, whether some net will have more number of fan outs. So we should avoid those fan outs. So we are inserting some buffers to avoid HFNS. So we are doing the HFNS. Next, we are taking for timing or power optimization. So for this, we are doing some cell sizing. So we are upsizing or we are downsizing. So upsizing means the delay will be reduced, and downsizing means the delay will be increased. So these technique we are following. Then BT swapping. So we have a lot of BTs. So HVT, LVT, ULVT, ULVT, LL. So these things we are swapping in these stages. So ULVT will give more leakage, but timing will be good for using ULVT. And LVT we are using both the leakage and the timing as well as it was equal in using LVT. So HVT it's only used at leakage. So timing will be violated by using this HVT itself. So these things will be added after HFNS stage. Then scan chain reordering. So for example, one flop is sitting near here, this end, another flop is sitting that end. So the interconnect length will be more, the detouring will be more. So due to this also we are getting some timing violations. So for avoiding these things, we doing scan chain reordering. So it will connect net to one flop to nearby flop. So these are the stages we are following in placement. So goals of placement is timing and power and area optimization. And we need to avoid some congestions. So if it is more congestion in placement stage itself, we will get more thoughts in routing stage. So we need to avoid those things in placement stage. Particularly, we will see congestion and timing in placement stage. So it should be avoided. It should be reduced. So this is the initial or global or course placement. So how the standard cells are sitting in rows can able to see. So it will not not a proper way. Okay, the standard cells will sit uh, not seeing any particular location. Okay, it will be overlap. So this is the course placement. So legalization only, the standard cell will sit in a particular standard cell row with the proper spacing. So this is legalization step. Okay, for after that we are putting some placement blockages. So in floor plan stages also we can do that. In placement stages also we will do. So placement blockages, particular we will have three types. So soft blockage, hard blockage, and partial placement blockage. So hard blockage, we are putting some hard blockage in particular area means there is nothing will sit in that particular area. Okay, standard cells or macros, anything will not sit in that particular area. Soft blockage is it will allow some buffers or inverters in that particular area. So partial placement blockage, so we will saying the tool to sit particular percentage, 60 percentage standard cell sit in that particular area. We are saying the tool to do some partial placement blockage in that area. Will half of the will sit, half will not sit. So you can see the command create placement blockage boundary type partial blocked percentage 40. It means 40 is blocked and other rest is available for standard cell. So placement bounds, it is also a like placement blockage. We are putting some placement bounds. We are saying the tools to with the particular standard cell in that area. So these are the major steps we are using in placement stage, place opt and refine opt. So place opt, we are place opt, the command will do course placement, legalization, HFNS optimization, legalization. So refine opt, if we have any further congestion or timing will not improve, then we will do this refine opt stage. So congestion. So in placement, we will see congestion and timing. So what is congestion? If available number of routing resources is less than the required number of routing resources. So in a particular area, I want 10 routing resources, but I have only 8 routing resources. So what happened means the routing resources was less. So due to this, the standard cell will not sit in that area. More standard cell is sitting in that particular area. What happened? It's said to be a congestion. Okay. So congestion, how it means the routing resources will be a less in that particular area. It's said to be a congestion. Okay, we need to avoid that congestion. How the congestion happening? Mostly the congestion happens due to pin density or cell density. Okay, the cells which are talking near the cells which are talking to the macro will come and sit nearby that particular macro. So that what happened means the cell full 1000 cells are sitting near the macro. What happened? The overlapping, the congestion will happen in that particular area. So we need to avoid that. What we'll do means we'll do some partial placement blockage. Okay. So for pin, for example, AI, OAI cells will have more pins. So due to this, these pins, these cells, we have more pin level congestion. So we need to avoid that. So we are using some halos or some other techniques we are using for to reduce these congestion. So high cell density in a small area, then pin density due to AOI cell. Then we are doing the floor pan badly. So these are some reasons for creating congestion. So these are the technique we'll use to reduce the congestion, cell padding. Then we are rerunning the place opt. So changing the floor pan, reordering the scan chains. So HFNS is nothing but a particular net will have more number of fanouts. So we need to avoid that. So that we are inserting buffers to the higher number of fanouts which have, we need to source that net and we need to insert a buffer for that particular net. So that the HFNS will be avoided. Then scan chain reordering. So this is the scan chain reordering. So the cells is sitting here and it is talking with far away flop. So that the timing will be violated and congestion also will be more. So we need to avoid that. So we are connecting the net to nearby flop and we are connecting to nearby puck. So by changing the scan chains, we are avoid the congestion in further stages. So after these things are done, we need to do placement optimization. So placement optimization, what we are doing means cloning. We are duplicating the gates, then gate sizing, swapping. So these things will do in place of technique. So that the congestion and timing will be more great when compared to a before stage. So till this, any doubt?
Participants, if you have any doubts, you can ask.
Yeah, I have covered floor plan, power plan, and placement. Yeah, so next we going for CTS. So before placement stage, we not have any clock, real clock. The clock will be ideal. So the timing will not be accurate. So after CTS only we are building the clock. So the propagation will happen. The timing will be a the timing, the accurate timing will be seen after CTS only. Okay, before CTS we will check setup. Setup depends on max delay. So after CTS only we are seeing both setup and hold. So setup, so I will say that things after this completion of CTS. So CTS is nothing but we have more number of sequential circuits in our design. So flops, registers. So we need to give the clock equally to those particular flops or registers or sequential circuits. So CTS is connecting those clocks to all the circuits. So what is the aim of the CTS? So we need to balance the skew and minimize the latency. Okay. So skew is first of all I need to say latency. What is the latency? So the PLL is there. So one flop is there. So the time taken from PLL to one flop, the time taken for a clock to go from PLL to one flop is latency. Okay. So skew is nothing but we are taking two different flops. We are subtracting those time. Okay. So from PLL to one flop getting 10 PS means another flop is going for 8 PS. So we are latency 1 minus latency 2. That is skew. So we need to achieve this skew and latency in CTS stage. So CTS target balancing the skew and reducing the latency. So CTS goal max tran, max cap, max fan out. So tran is nothing but the time taken for a signal to go from 0 to 1 or 1 to 0. Okay, that is the time. That is the max tran. Okay, max capacitance. Max cap means the how much the load can able to uh, drive for a particular net. Okay, fan out. Fan out is nothing but the output, how much number of input it can able to load carry. So inputs for plus CTS. So we have placement diff, then target latency skew. So buffers and inverters for building the clock tree. Then clock tree exceptions. So these things, NDR rules. So double with the double spacing, those things are needed for input. So output CTS step latency report, timing report. So CTS optimization. So this is the clock. Okay, this is the clock port. This is the PL. So my flops are sitting far away and nearby. Okay, my aim is to distribute the clock equally to all the flip flops which are in my block. Okay, so by applying this, my skew and latency should be balanced. Okay, so in 180 nanometers, we have used one single point CTS. So nowadays, 1 point in nanometer are going. So now we are using multi-source CTS. What happened means before we have one port, one clock port. So the skew and latency was not achieved. So nowadays, multi CTS. What happened? The single port will communicate to DOPs. The DOPs were surrounded by the full block. So the distribution of clock will be equally divided to all the sequential elements in our block, so that we can able to achieve the skew and latency. When compared to 180 nanometer, we are getting good results in 1.5 nanometer. So we have different types of clock tree, H tree, X tree, so that we can able to build the clock. So this is in depth can able to. So after doing CTS, we need to do optimization techniques. So what are the optimization techniques we are following? So buffer sizing. So we need to upsize or we need to downsize these things. Then gate sizing. Then level adjusting, buffer relocation, gate relocation, dummy load insertion. So these are some optimization technique we are following in CTS opt. So this is the latency thing. So this is the PLL. So on one flop, I'm getting the data will be sending with 8 PS. So another flop getting data by 10 PS. So latency is divided into two types. So source latency and network latency. So source latency is from PLL to clock definition point, and from clock definition point to sync pin of flop is network latency. So in architecture level, so we will have source latency. So the block level will have network latency. So when we are doing projects, so block level we need to uh, fix the network latency. So next is crosstalk noise. So this is very important after CTS stage. So we have n number of nets. Okay. So one net will have high drive strength and another will have less drive strength. Okay. So victim is a one net, it will have less drive strength. So aggressor is a net will have more drive strength. Okay, due to high drive strength net, the another net will be violated. Okay, due to this, the noise was created. So noise is refers to unintentional effects between two signals. Okay, so due to coupling capacitance between two nets, we are getting the crosstalk noise. So we need to avoid those noise in after CTS stage. So glitch is also one type of noise. So next is crosstalk delay. So when it is due to input transition of victim, it's due and it's due to input tran of aggressor net, we are getting this crosstalk delay. So crosstalk and positive crosstalk, negative crosstalk, we need to avoid those things. How we need to avoid? We are using NDR rules. Okay, between two nets, we need to use NDR rule. That is double spacing and double width. Okay, so we are giving proper spacing. We can able to avoid the crosstalk. Then we need to increase the drive strength of victim net and decrease the drive strength of aggressor net. So then we are jumping to higher metal layers. So the net was routed with the M8 means we need to go for M15 or M16 so that the higher layers will have more drive strength than compared to lower net. So shielding, we need to shield seal the particular net. Mostly the clock net we need to shield. So DRV violation. So max tran, max cap, max fan out. Okay. So how the max tran was fixed by replacing HVT cells with the LVT cells, then upsizing the driver. So upsizing means it will reduce the delay so that we can use. Then HVT cells, replacing HVT with LVT. Why we are replacing HVT means HVT have more time, it will have more timing violation, but it will good for leakage power. So reducing the net length by adding buffers. So if it is more, the net length was more, inserting the buffer, so the delay was reduced. Obviously, we know that delay equal to RC. So we reduce the resistance and capacitance. The delay was reduced. So we are inserting the buffers in between nets. So max cap, max fan out. So this is the max fan out. So this is the splitting. So cloning means, so we are inserting some buffers. So it is duplication, like duplication. So same drive strength. If it is 5x means 5x we are inserting, and we are doing some splitting. But buffering, we need to take a new buffer. So 2x means we can take 5x or 7x. So by these things also we can able to avoid this thing. Next is the routing. So before that, we need to know what is routing. So routing is
creating physical connections based on logical connectivity. Nothing but we are creating the nets. Okay. Before that, there is no nets. It is like visual. Okay. So in routing stage only, we are getting the real net, real physical connections. Routing creates physical connections to the clock and signal pins through metal interconnects. So this is my block. Okay, the block was divided by grid. Okay, so due to this, the routing was done by based on the grid. We are placing the macros based on this only. The routing was done. The track, the nets was created. So we steps in routing: global route, track assignment, detailed route, search and repair. So in global route, what we are doing means we are dividing our block into G cells. Okay, so G cells will have the same height and width of global connectivity. So here we are allocating some metal layer and we are dividing the cells into some three types. So second is global route review. So global route, we are trying to fix the PG and we are able to allow the placement blockages and routing blockages. So track assignment, we are creating the tracking in this stage. So track was created and overlapping was avoided. So in this stage itself, we are checking the DRCs and signal integrity and timing related violations in track assignment stage. So next is a detailed routing. So detailed routing only we are doing accurate routing. In global routing, we are doing approximate routing. The approximately that the nets are allowed. In detailed routing only, we are doing logical connectivity. Logically based routing will be done in detailed routing stage. So sets and repair. So any DRC violation, any spacing violations is there, we can able to resolve in this sets and repair steps. So after routing was completed, we need to check DRC, LVS antenna violations. So for antenna violation, we need to fix by using antenna diodes or any metal hooping or any WVR insertion technique. So these are things we will follow. So next is sign up 6. So PNR was completed. So after PNR, we need to do some sign off checks. So first we need to do timing calculations, STA, then PV, physical verification, LVS, CRV, these things. Okay, this will be a depth. North opens we need to clear. So EMIR, those things. Okay. So till this, and so any doubt till now?
Sir, what is the scope for machine learning implementations in the physical design process?
Yeah,
Do you have
actually,
any scope there?
yeah. So actually, NVIDIA have started AI based VLSI chip designing. So it is in process only. They are building a machine learning and AI techniques for these floor planning for placement things. Now it will come. They are people are saying it will come, but still it's not done. But research is going on.
Okay, sir. Sir, in the complete entire PNR process, in most of the
Hello.
examples, hello, am I audible, sir?
No, ma'am. Yeah, no, it's not.
Okay, sir. In the complete PNR process, most of the challenges are being faced in which part of the stage, sir?
Ma'am, in all
Maybe
the stages we will face.
near tape
Okay.
outs, I think you
Yeah.
might have observed, no?
Yeah. Actually, in PNR, from floor plan to routing, we'll do some wrongly anything. Example, we're not checking any congestion. Okay. In sign off stage, it will be big issue will come. So starts it will come 1,000 starts, 2,000 starts and all. So in the initial itself, we need to do first of all, floor plan should be a good basement when we are building some house. Okay, the proper way is basement should be good. Okay, basement is not good. What happened? The building will not be strong. Like that only, the floor plan should be a good. Hello.
Okay, sir. Thank you, sir.
Yeah. Yeah. Any other doubt?
Dear participants, any other queries?
No, madam.
Okay. Thank you for your time, professors. Thank you.
Okay, sir. Thank you for accepting our invitation for our FDP, sir. On behalf of our Department of ECE, I would like to extend our gratitude for exemptional lecture on synthesis in VLSI design, sir. Your
Yeah.
in-depth insights into cell placement, power optimization, and congestion management were highly valuable and provided holistic understanding of the synthesis process, sir.
Yeah.
The way you illustrated the interplay between these critical aspects and the impact on overall design efficiency is enlightening, sir.
Yeah. Ma'am.
Participants greatly appreciated your practical approach, especially your discussions on the strategies to minimize the congestion and network issues, optimize power consumption without compromising the performance of the system. So, thank you for your dedication, expertise, and willingness to share your knowledge among us, sir. Your session was not only informative but also inspiring for everyone in attendance. We look forward to future opportunities to learn from your experience, sir. Thank you so much.
Thank you, ma'am. Yeah, I have attached my mail ID in chat. If anyone needed, can please take.
Okay, sir, I will share.
Yeah. Thank you, ma'am. Thank you.
Participant, all of you, if possible, all of you switch on your cameras for photo. Uday sir, please switch on your camera for group photo.
Yeah. Yeah. Yeah, 1 minute. I got it.
Okay. Thank you, sir. Thank you,
Yeah. Thank
everyone.
you.
Okay, tomorrow all of you join at the same time, 6 p.m. sharply, and you can leave now. All of you fill the feedback link. After 9:30, you will not get the feedback link. Please fill it immediately.
Okay,
Thank
thank you,
you,
madam.
everyone. Thank you. Thank you, everyone.
మా రికార్డింగ్ స్టాప్ చేసేస్తాను.
Okay, sir. Okay. Stop చేసేది.